let's have a quiz on Thursday. Just so, I don't know, on something. HBA was already postponed. So the test is scheduled for Thursday next week. So I figured a quiz before the test would probably be good to get ourselves kind of warmed up and honed in on so today we'll plan to all right, so back to this business about our exam. We have an exam next Thursday, and we got to try to squeeze in some information. So today we're going to talk about the last part of Green's theorem, which addresses the boundary value problems, and then we'll begin our discussion on applications, and that applications are in Chapter 5. We are going to focus our applications on spring applications, where we're looking at initial value problems, which is why this part is a little probably important for us. And our main focus will be on, we'll begin like we did in Chapter 4. We'll begin with homogeneous differential equations, applications for homogeneous differential equations, and then we'll tack in an external force in the spring. And so we would be looking at non-homogeneous differential equations and looking at initial value problems that address those so that we can apply Green's theorem. Now, the boundary value problem applications go in the next section in Chapter 5, 5.2. And I don't know how much of that we'll address, but I feel like we should talk a little bit about boundary value problems for higher order differential equations, which our Green's theorem tool will make it easier for us to solve. If you call this easy, right? So that's our focus today, is to do the boundary value problems for Green's theorem and some applications. We'll do more applications next time. We'll start reviewing. And I hope to have a review sheet for you so that you can try to anticipate what's going to be on the test next week. Yes? The quiz will probably focus on variation of parameters. That would be next class. Yeah, we'll have that quiz for next class.
That doesn't include the Cauchy-Euler, right?
The Cauchy-Euler, no.
Which chapters are
4.3, 4.4. I don't know. If we really need to know, it is 4.6, correct? Okay. Probably one. Well, you know how long these things take, right? Yeah. All right. So our focus today will be on the last bit of Green's theorem using a boundary value problem. So this is how, actually, the book kind of begins a little bit differently, but this is where they end up. And the boundary value problem addresses, instead of having an initial condition are conditions on one particular x value, one particular independent point value. Instead of addressing one independent point value and finding out like y and y prime of that, the boundary value problem addresses 2 points. A and B. So as a comparison, an IVP would have conditions YA is equal to some number, and then Y prime of A is equal to another number. And so the initial conditions focuses on one X value. The boundary value problem, the boundary conditions are not exactly given like this. More like the BVPs kind of look like either Y of A equals a number and Y of B equals to another number, or Y prime of A equals to a number and Y prime of B equals to another number. So usually boundary value problems focus on a particular Y or Y prime, and then they figure out the values at two different independent points. And sometimes a combination of these things. And what they tried to do, or what they want to stress in the book, is that this system, or possible combinations depending on what A1 and A2 are equal to, can mimic one of these boundary conditions by letting, for example, if we let B1 and B2 equal to 0 or something like that, then we have a boundary condition that looks like this first one. Right? If B1 and B2 are equal to 0, then any information about the Y prime gets lost. And so we're just focused on information about the Y itself. And for simplicity's sake, they want to look at this when it's equal to 0 to make it easier for us. But in more applied problems, they may or may not be equal to 0, which can complicate things quite a bit. All right. Without going into the background of it, what happens here is that you would do similar to variation of parameters, where you would find U, U prime, U1 prime, and U2 prime, and then take the antiderivative using Wronskians and stuff like that. So without going through all that stuff, we'll just say that they came up with the Green's function for this. If we're interested in finding a particular value, and we have to kind of be careful about how it's structured. So initially, it looks like it's structured kind of like the same way that we would see it, that the Y of X is equal to this. But there's something tricky here, in that Green's function is not that nice function that we saw earlier, function of X and T. Instead, Green's function is actually a piecewise function. And notice that Green's function from before had an X as a limit of integration. And now I don't see the X here. What happens is that Green's function is going to split up its piecewise function with an arbitrary X in between, whatever that means. So that means Green's function is going to look like this. So keep in mind, our variable x, y is going to eventually be a function of x. And so the g of xt, the Green's function, is going to have some x's in there that we can, treat as a constant with respect to t. We could take them out of the integral, but then we'll also need the functions of t as functions where now the limits will split that up into two different integrals. And there's one more strange thing that happens here that I won't really talk too much about, but if you remember Green's function, there was a minus sign in there somewhere, but here the minus sign got lost. What's going to happen is that we're going to create integrals with limits that involve these x's, And when we do that, there'll be a switching of the limits that's going to negate your x value. And so that's why we don't see a negative sign here. Okay, so this is a setup for your boundary value problem. And I think what's important for us is to find out your y1 and y2. And if you remember, y1 and y2 are solutions, are fundamental solutions. To the homogeneous differential equation. So the homogeneous differential equation has fundamental solutions that we've solved for before, and then we get that, and we get the W is the Wronskian. And then now, instead of going from x naught to x, and because we don't have one initial condition, we have boundary conditions, we're going to let that be the boundary limits, and then our varying independent variable will be between a and b as part of the integral. All right. I think it's best to jump into a problem and see where we go with it. All right, let's take a look at the problem. I hope not, because I need to start talking about applications. So we'll see. Let's take a look at a problem from the exercise section in this part of the book. We have y double prime minus 2y prime plus 2y is equal to e to the x. That's your differential equation, your non-homogeneous second order linear with constant coefficient differential equation. And instead of y of 0 equal to something and y prime of 0 equal to something else, we actually have y of 0 and y of pi over 2 as your boundaries. So 0 to pi over 2 would be your boundaries. So already you can identify certain things here. Our 0 is our a. Our pi over 2 is our b. We have our function f of t here as e to the t. And then we need to figure out what y1 and y2 are based on our homogeneous part of differential equation. So let's start with that. So when you're going through a test, a problem, if you don't know where to start, just suppose it's equal to 0 and then see what happens. So let's start with that. Y double prime minus 2y prime plus 2y is equal to 0. This is a homogeneous differential equation. We should know the solutions to this. What are the solutions to this? Let's see. This is assuming this is not the Cauchy-Euler equation, right? This is back to the simpler one where you assume your solutions are e to the mx. And you have to solve for m. We have an auxiliary equation. And your auxiliary equation are m's matching with the powers and the degrees. So m to the first, or m squared minus 2m plus 2 is equal to 0. And then if you can't factor this, can you factor this? Can't factor it. Let's use the thing. Quadratic formula. Thank you. 2, so negative b plus or minus the square root of b squared minus 4ac it's negative, but this is a negative, so negative negative will be a positive. The b squared will be positive. And the a is 1, so this is 2a. So we have positive 1 plus or minus 2i? Two I over 2. So we have complex conjugates for our roots, and I hope you're comfortable enough to say, okay, then my y1 and y2, the solutions are going to involve e to the x sine x, e to the x cosine x. Okay, so we have our solutions. So now that we have our solutions, we want to make sure that they fit into our conditions. So if we try to like put y of 0, which should equal to 0, and y of pi over 2 should equal to 0. So let's see. Let's check to make sure our conditions are satisfied. And that's what makes it nice for us, because these things are all equal to 0. Having these equal to 0 makes Green's theorem move a little smoother. If they weren't 0, then we'd be in a little bit more trouble. So y of 0, e to the 0, cosine. What's cosine of 0? That's 1. So e to the 0 is 1. So this is 1. That didn't work for our a, right? So we have a little bit of an issue there already. Let's try y of 0 for the second one. I hope it works here, because if it doesn't work, then we might be in trouble. E to the 0, what's sine of 0? So that worked out. Okay? All right, so this is a quick check that you need to make, because the fundamental solution that works for the A portion, that works for the first boundary condition, has to be y1. So at this point, I kind of just randomly said y1 is equal to this, y2 is equal to this. But now I'm going to have to switch it, because my y1 didn't work for my first boundary. I hope it works for the second boundary, but I know that my y2 works for the first boundary, so I'm going to want this to be y1. Yeah. So let's make a little note here, especially because this didn't work. Let y1 equal to e to the x sine x. Now let's check y1, or let's check this other function to see if it satisfies our second boundary. Y of pi over 2 evaluated, e to the pi over 2 is not 0. What's cosine of pi over 2? So that is 0, so that works out. So this would be, fittingly enough, y2. So because of those boundaries, and because of the fundamental conditions that we have to satisfy, fundamental solutions that we got that need to satisfy those boundaries, we just have to do a quick check to identify which one is our appropriate y1 and y2. We good? Okay. So now that we have y1 and y2, according to our formula, we need to figure out the Wronskian and then this thing. So let's get that set up. Let's get our w figured out. Oh boy. y1, e to the x, sine x, e to the x cosine x. So the derivative of e to the x sine x is, well, it's going to be derivative of the first times the second plus the first times the derivative of the second. So I'm just going to factor out an e to the x. Derivative sign is positive cosine, right? All right, next one, derivative of the first times the second plus the first times the derivative of the second. Derivative of cosine is negative sign, and I factor it out, and e to the x. So that if we take the determinant, we have e to the 2x. We got sine and cosine minus sine squared. So that's a diagonal. The wings, we got e to the 2x again. We can factor that out. Let's factor that out. So e to the 2x. And then sine and cosine again. And then plus cosine squared. I hope this simplifies. We got sine and cosine with opposite signs. And we got negative sine squared minus cosine squared. Factor out the negative, and you get sine and cosine, each of them squared, so that's 1. So we got the negative sign that we factored out. We got e to the 2x times, and then we got sine squared plus cosine squared, which is 1. So this is our Wronskian. Okay? The negative came from this negative sign right here, which was so let's write Green's function in green. Well, no. Remember, Green's theorem kind of summarizes W1 and W2, and that's how it turns out to be W1 and W2, and so Green's theorem kind of extends those ideas so that we don't have to remember the W. The W1 and W2, if you're doing variation of parameters, then you definitely want to figure that out. But some people actually have it memorized already, because one of them is going to be 0, and so it'll end up to be one of these terms anyways. But Green's theorem allows us to now, instead of doing all those Wronskians and stuff, we have a special formula for it, and it takes that into consideration already. So Green's theorem is going to come in a couple of pieces. The first piece is going to be the y1 evaluated at t. So it's a function of x and t. y1 evaluated at t, so e to the t sine t. Y2 evaluated at x, e to the x cosine x. And then we're dividing it by the Wronskian, which we found to be a negative e to the 2x. And this is good for t values between 0 and x. So we're going to create, when we create our integral, we'll see how that fits in to this piecewise Green's function. So the second part of Green's function is taking y1, evaluating it at x, and taking y2 now at t. And the Wronskian's all at t, because they need to be part of the integral, which is wrong here. It should be e to the 2t. The second piece takes a look at y1 and then evaluates it at x, so that's e to the x sine x. And it takes y2, evaluates it at t, e to the t cosine t. divided by the same Wronskian e to the 2t. And this is good for t values that go up to the second pi over 2. And x values, we'll pick up the integral from the x that we left off from the last function. So this is Green's function. Are we good?
Are we done?
No, we're far from done. We're not far from done. We're about halfway there.
How happy would you be if you got there?
I would be happy if you got here, but I would be happier if you go further.
Is x going to stay as
Yeah, x is going to stay in terms of x, because when we eventually solve for this integral, we will integrate this, and to integrate this, we'll have to break it up to two different integrals.
What's that?
This is how you use Green's function to find a particular solution. This is our next step, yes. And it looks innocent, but when we actually, when you, it doesn't look innocent. When you integrate a piecewise function, you have to actually break up your integral, and that's what's going to happen. And we want our final answer to have an x in it. And so those x's that are floating around in here is going to play a part in our values.
You do that because it's a spring?
Well, this is, I don't know if they're good examples of spring boundary problems, but this is because we have information about the function at the boundaries instead of in one point. Okay, so this is what we want. We want to integrate that. We want to integrate it. Oh, not only Green's function, but we have to integrate it with f of t in it. So f of t is this thing, the non-homogeneous component. So our integral then, let me write the integral first. Our y of p then should look like an integral from 0 to 2 pi. Oops, not 2 pi, sorry. 0 to pi over 2. Green's theorem, I'll just rewrite g of xt times f of t. I figure out what's f of t. E to the t. So it says e to the x, right? So we just make sure it's a function of t, and then dt. Yeah, it looks innocent, doesn't it? Yeah, right. Yeah, I have to put in all that stuff. So I think it'd be nice to, I don't know, do you guys look at the sheets, the notes online? Is it good if I go further down and create more space, or should I start this on a new page? Yeah. Yeah, I think if I start scrolling down here, then this thing kind of shrinks so that it'll fit something. And so, okay, I'll go new page, which means I need to copy this. So here's our continuation. Here's our integral that we need to do. I think before we actually just put it in, I think there's some simplification that can happen here. Let's rewrite our Green's theorem or Green's function. We should have done this in the previous page. One of the e to the t. So this will end up being a negative. The e to the t will cancel here. We have sine t over e to the t times e to the x cosine x. So this will allow me to, because I'm going to be integrating with respect to t, I'm going to get all the stuff with the x's in it and move it outside of the integral anyways.
So don't we have to have t in the denominator, we have t, and then the numerator we have e to the n.
I have e to the x here, but I also have e to the t here, and so that's what I canceled. Is that? Okay. All right, and so this is again from 0 t to x, and then if I do the same thing here, I'm going to be able to cancel out one of those, and I have e to the x sine x is going to be a constant with respect to t inside of that integral, and I'll have a negative sign also, and then cosine t over t, or e to the t. This goes from x to pi over 2. So given that, our integral is going to have to break up into two pieces. Our integral, instead of going from 0 to pi over 2, our function changes at some x. So it'll change from 0 to x, and then I'm going to put this in later, and then x to pi over 2. So this is how I'm going to break up my integral, because according to my function, I have it in pieces, and it breaks off at x, and so this is how I'm going to break my integral up. You guys remember this from Calc 2, right? Okay. So now I'm going to pick up these functions and drop them into the appropriate places, right? But as I drop them into the appropriate places, oh, and I also have to multiply by e to the t. But as I do that, I'm just going to take my e to the x's, all the x's outside of that integral. So here's how it's going to look like. E to the x cosine x gets taken out of that first integral, going from 0 to x. So what do I have left? I have minus, I guess I should take that negative sign out as well. So let's take that minus sign out. Minus sign, e to the x cosine x is gone, so I have sine t over e to the t, but then I also have to multiply by f of t, which is e to the t. Oh, good, they cancel. All right, that's not so bad. All right, so we can do this in our heads, but we'll do it in our next step. Our other integral is going to be another negative. I'll factor out again an e to the x sine x, all the x's gets taken out of the integral, and this time this integral is going to go from x to pi over 2. And inside I have a cosine t over e to the t times e to the t dt, and the e to the t's again would cancel. And so now I have the integral of cosine from x to pi over 2. Let's figure those out. First one I'm assuming is easier because there's a 0 in there. The antiderivative of sine is positive or negative cosine? Negative cosine. So this is a minus cosine t evaluated from 0 to x. So if I put x in there, I get a negative cosine x minus negative cosine of 0. So it'll end up being a plus 1. So what do we have? We have a negative e to the x cosine x times negative cosine x plus 1. Should we keep simplifying this or come back to this after we integrate the second one? Come back to it. Okay. Second one. It's just a cosine. Antiderivative cosine. Positive sign. So we got sine t, where t gets evaluated from x to pi over 2. The order is important. What's sine of pi over 2? 1 minus sine x. So we got 1 minus sine x. And this one has a plus minus, so it's a negative e to the x sine x times 1 minus sine x. suppose we can leave it like that, but we could simplify it also, maybe. So let's simplify it. Let's multiply everything out. Negative, negative is a positive. I have e to the x cosine squared x. And then this negative and the positive is negative minus e to the x cosine x. What? I'm done. People want me to simplify. The next one is minus e to the x sine x. Minus minus is a positive. E to the x sine x times sine x is sine squared x. And it looks like another sine squared and cosine squared business. So if we put them together, factor out an e to the x, we then would have a positive e to the x minus e to the x cosine x minus e to the x sine x. I think we're good here. So it didn't take the whole class period. Say that again? Oh yeah, this is YP. No, because this is a boundary value problem. So with a boundary value problem, you're looking for just the final answer. So this is it. This is your particular solution. Yeah, well, we kind of took care of those questions over here where we figured out the Y1 and Y2 business, and then we got them to equal to 0 at one of the boundaries. Okay, good. I hope it's right. Yeah, that's right. Let's move on. Wait, is it a 41? It's an odd number. It's just scary. This is 4.8. This is the review. It's 4.8. Number what? 41. Oh. All right. You must be experts now. Okay. Are we good? Looks like it's right. So there's another example here that would correlate with your homework, but I think I'm not going to do it because it might take the rest of the time. And I want to get started with the applications. So good luck with your homework. Let's jump to some springs. Those spring problems, I don't know if we remember those spring problems back from chapter 3 or something where they introduced those springs. And there are some simpler spring problems, and then they can gradually get more complicated. So let's take a look at some of the spring problems that they have here. And they broke it down into subsections. So section 5.1 is broken up into 3 subsections or something, 5.1.1. 0.1.2 and 0.1.3. And each of those kind of focuses in on a particular type of spring problem. So let's start off with an undamped motion. And actually, before talking about undamped motion, they talk about springs in general. suppose we should. Talk about modeling these differential equations, these springs with differential equations. So let's see, a spring hanging down. Oops, that's not it. So a spring hanging down, you pull the spring and you let it go, and then there's some stuff that happens to it. Okay, it oscillates. So I think in Calc 2, when they start talking about these spring stuff, they use Hooke's law as a very, very simplified differential equation where you let it go and then you assume that there's no friction and it oscillates forever, and they have a nice oscillation problem and where you just get to integrate something. Well, with differential equations, you can actually, because those ideas came from differential equations, you can actually use differential equations to kind of map this out. And what happens here is that they use Newton's second law, and then they have this differential equation, the force, trying to express the force as mass times acceleration based on whatever else scenario you have on the outside. So if you're talking about a spring that, I guess you have to say that it lives in a vacuum where there's no air resistance and there's no restrictions on friction or anything like that, it just starts to oscillate and goes on forever because there's nothing to slow it down. So that idea where it doesn't slow down is an undamped motion. You don't damp it, there's no friction, it just goes on forever. And the damping happens well, let me just copy this because when there's no damping going on, the damping is going to, the friction is going to slow down the velocity, and the velocity is the first derivative of the motion, right? So without any damping, you don't have any friction happening, and you don't have anything. Your differential equation should not involve your first derivative, and so the force is just going to be explained by the actual motion itself. And so we have a differential equation that has a second derivative in the original motion, x, without the x prime. So your differential equation would look like this. So this is for an undamped motion. And then, so all that's left to figure out is what your spring constant is to be able to help us solve for this. Can you imagine what the solution to this differential equation is? If you just look at this as a math problem, I have y double prime, or my x now, be careful how they're using this. So x is your dependent variable, so instead of y you're using x, and then t is your independent variable, so instead of x you're actually using t. So given your x of t and your solution that you're going to come up with x of t, can you imagine what your solution might look like here, just by looking at it? Sines and cosines, right? If you were to think ahead, and this is one of those things where it might be good for you to think ahead when you're looking at problems on the exam so that you know what to expect. If you think ahead, looking at this differential equation, this whether you do this in your head or you write it down, this is a second order differential equation with constant coefficients. It's homogeneous, so we're going to go to that auxiliary equation business. And the auxiliary equation is going to be m squared plus omega squared is equal to 0. And omega is a constant, and you're squaring it. It's positive already, but you're going to square it to make sure it's absolutely positive. So it's a positive number, and you're going to be left with a couple of complex conjugates for this root, right? Because you bring the omega on the other side, it'll have a negative, and then you take the square root, and then you'll have i's and stuff like that. So you'll have complex conjugates. So if you thought about this far, what are your solutions when you have complex conjugates? Sines and cosines, right? And but the other nice thing about this is that not only do you have complex conjugates, but there's no real parts in these complex conjugates. So if you solve for this, you get m squared is equal to minus omega squared. So m is equal to plus or minus omega I. There's no real parts to this. And the real parts would be sitting as an e to some power. That would kind of either damp this or make it go exponentially up higher or whatever. So it does something weird to it. But there's no real part to it, and this is all imaginary. So from this idea, we should know that the solutions are sines and cosines. In fact, the omega will be the coefficients of the sines and cosines. So your solution then for an undamped, oh, I didn't write the solution down. Well, you know what it is. Your solutions then should be what would it be? Sines and cosines. So y equals c1 sine omega cosine omega t, we're using t now, plus c2 sine omega t. And then if you have initial conditions or boundary conditions for that matter, you should be able to solve for it because we just plug in those values. Okay? Do we need to use Green's theorem for this? I'm asking, do we? Why am I asking? I'm just to make sure that we're all on the same page. No, we don't have initial conditions or boundary conditions. And what else? What kinds of problems do we address with Green's theorem? Initial conditions or boundary conditions, and then also non-homogeneous. So this is a homogeneous, so let's not bother thinking about Green's function for this. Okay. I don't know. My notes have examples. I don't know if we should do an example. This is really easy, right? You can figure this out. All right, let's go to the next type of a more interesting one. Maybe we'll do an example of this, is when we have a damped motion. And with a damped motion, our first derivative is going to play a part in this differential equation because you have something slowing down your velocity. Friction is going to slow down your velocity. So we need to incorporate the first derivative, and then now your differential equation is going to look like this. And so what they did over here is that they used symbols like, they came up with omega as something to do with k over m. You guys know what omega is, right? Yeah. Something over the mass. So when they introduced the damping over here, the friction damping, they have just some positive constant. It's minus a positive constant times the first derivative, the velocity. And when they bring it over to one side to make it look like as a standard form or general form or whatever it's called, differential equation of some form, they change the notation. Instead of calling it positive beta, they call it 2 lambda, because lambda apparently looks nicer. Some reason. So anyways, we have a differential equation that looks like this, and if a differential equation looks like this, it would, again, first order linear with constant coefficients, homogeneous, so it follows that we're going to look at our auxiliary equation again. Sorry, second order. Second order linear, constant coefficients, homogeneous. And so we have our auxiliary equation. And our auxiliary equation looks like m squared plus the constant 2 lambda times m plus, and then the constant omega is equal to 0. And so when you look at this, because you don't know what omega and lambda is, they're right now general form, we're going to just use our thing. Minus b plus or minus the square root of b squared minus 4 ac all over 2a. And then we come to this generic roots where we have the discriminant, and depending on what the discriminant is, that's going to dictate how our solutions are going to look like. Okay, so if we focus on our discriminant, if this discriminant is all positive, then we have 2 distinct real roots. If it's equal to 0, then we have 1 repeated real root. And if it was less than 0, then we have complex conjugates. Okay? So let's take a look at the discriminant and look at those 3 possibilities. And imagine, if this is where I'm asking you to think ahead to see how our solutions would look like. So if, let's call it D. D is equal to just the inside, 4 lambda squared minus 4 omega squared. So if D was bigger than 0, and we got 2 real roots, and if we have 2 real roots, what would our solution look like? Thinking ahead, how is the solution going to look like? E to the what? E to the m1. So it's going to be some constant e to the m1 times t plus another constant e to the m2 times t. So we got a couple of exponential functions. Now, whether these exponential functions are positive or negative is going to dictate whether this is going to be in, growth or decay type of system. And so we'll just have to deal with that. Most likely, if this is a spring, right, that's being damped, we should expect this to be decay, right? So we should expect that our solution should be M1 and M2 are what? We should expect them to be negative, okay? And if they come out positive, then might have done something wrong. So if the discriminant was equal to 0, then we got 2 repeated real roots. And we can actually identify our roots, right? So what's our root equal to if the discriminant was equal to 0? Can you look at our m here? It's what? It'll be negative lambda, right? So the root is going to be equal to negative lambda. So remember what happens if we have repeating roots? There's an x for the second one. So the first one would just be e to the negative lambda t plus t times, oops, let's call it c2, t times e to the negative lambda t. So there's an extra polynomial attached to one of the roots. And then if we take a look at this, this is another decreasing, and then this is also decreasing. Okay. So the third case, if d is less than 0, we have complex conjugates. And then our solutions then would, we could probably try to figure out what the solutions are. It'll have something to do with lambda here. And I think it says in my notes, but well, yeah, it says in our notes. But it'll have a sine and cosine. So it'll have C1, some e to something, and then a combination of cosine and sine. Sorry, are you guys writing this down? Because there's a nicer copy of this in the that I'm going to put in the next page. But anyways, the sine and cosine is going to have this thing oscillating. So this will oscillate. But there is this function outside of the sine and cosine, an exponential function, which is, we'll see that the star over here is going to be negative lambda again, and that is that has something to do with the damping factor, right? So this is going to get damped. Now, depending on how damping happens, your oscillation may oscillate and then eventually get damped and still oscillating. But this will form like they call it an envelope. Have you heard of envelope, or am I just making that up? Maybe I'm just making it up. I don't know. Some envelope that keeps the oscillation within those exponential functions. So it still oscillates, but it's going to oscillate within those exponential functions. Okay, so these are summarized a little bit better in the book and in my notes, where you have a nicer typed up version of the different cases. And they have special names for them. If you just get real numbers, 2 distinct real numbers, this actually squashes it down. It doesn't even oscillate. It just goes down and follows your exponential curve. This is an overdamping. Okay, it doesn't even get to go below the x-axis or anything like that. It doesn't get to do any oscillation. It just gets squashed down according to an exponential function. This is an overdamped. A critically damped one is the one that's damped kind of, it has one loop that it might go up, and then it's going to get damped down. And then the underdamped is when it gets to oscillate. It still gets damped down, like this weak-looking drawing over here. It still gets damped down, but at least it still oscillates within your exponential functions. Okay. So I think that is the more interesting one if we're looking at how this is damped. All right, let's see if we can do a problem in 5 minutes. There are, I don't know if I'm going to be able to do them. Let's see, number 21. So also, you guys are all taking physics where if it's in pounds, then you know how to deal with pounds, and if it's in like meters and kilograms and stuff like that, you know how to deal with the different things. Okay, a mass weighing 4 pounds is attached to a spring. We're not going to do this in 5 minutes. Let's just pretend. Okay, a mass weighing 4 pounds is attached to a spring. Whose constant is whose spring constant is 2 pounds per foot. Medium offers a damping force that is numerically equal to the instantaneous velocity. The mass of the initial release point released from a point 1 foot above the equilibrium position with a downward velocity of 8 feet per second. Determine the time which the mass passes through the equilibrium position, and find the time which the mass, what's the position of the mass at this instant. So essentially what we want to do is we want to find out, I think you can answer these questions without solving for the actual function, but if you solve for the actual function, then you can easily answer those questions. I don't know, we're not going to finish this in 5 minutes. Let's see if we can set up the differential equation. I think there's a homework problem like this in 5.1. Okay, let's see. So the mass is 4 pounds. So our differential equation should look something like this, right? So let's cheat and copy this. And then eventually we'll get them over to one side and figure out what the omega and lambdas are. So it'll make us, it'll give us a template to help us find our solution really quickly. So it looks like the mass is 4 pounds. So 4 pounds. So that's going to be our M. A spring whose constant is 2 pounds per foot. So the spring constant can be described is K, yeah. So the spring constant is K. So M is equal to 4 pounds, and the spring constant is 2 pounds per foot. Where else? A medium offers a damping force that's numerically equal to the instantaneous velocity. So a damping force that's numerically equal to the instantaneous velocity. So the damping force is equal to dx dt. And so numerically equal to that means it's just going to be dx dt without any other constants involved. It's not a factor of anything like that. So our beta in this case is just going to be 1. And then the mass is initially released from 1 point or 1 foot above. How would you translate that? Y of 0 is equal to 1 foot above, so we're going to look at the positive portion. Right? I'd like to look at up above as positive and below as negative. I don't know. Is that right? Is that a good way of thinking about it? And then initially this is pushed with a downward velocity of 8 feet per second. So y prime of 0, the initial velocity is it's 8 minus 8. Because it's downward, and we're establishing that up is positive and down is negative. So with a downward push, it's going to go downward push at 8 feet per second. So this should, we got K, we got beta, we got M, and we got the initial conditions. And so I think this is enough information to get us through the rest of the stuff. Okay, so we'll finish this next time. And quiz, did I tell you there's a quiz next time, right? Okay.